Our next speaker is Rudolf Roemer from University of Warwick. I hope my pronunciation is not terribly wrong. He's going to tell us about the
not any worse than what you did for Malte Röntgen.
Yeah. So he's going to tell us about the localization properties in disordered Lieb lattices and their extension. So let's welcome our speaker.
Right. Thank you very much. I'd also like to start for thanking the organizers for giving me the opportunity to show you some of our latest work. And I think it has been a very nice conference thus far, particularly this morning. And just to highlight some of the differences, I will be giving you a talk which is sort of a little bit more simple than the complicated interacting systems we've heard before. Namely, I will be talking about flat band lattices, Lieb lattices, where I will put in this order, and I'll be ignoring anything that has to do with interaction. And hence, in connection to what we just heard in the talk by Malte Röntgen, where he was concerned about actually constructing flat band states, I will use the disorder to basically destroy those compactly localized states. And then I will see what sort of happens to those compactly localized states when I put in this order. And the motivation here basically is that when in normal 2- and 3-dimensional systems, quantum systems, normal tight binding Hamiltonians, you put in on-site disorder, you can observe the phenomena of Anderson localization. And it was interesting to us to see what happens to those compactly localized states that are localized for a different reason in sort of the presence of the disorder that localizes because of the Anderson type of localization. So the work is done together with Jie Liu, whom you've heard give a talk on just the 3-dimensional systems already on Monday. And since her video didn't work, I thought I'd include a picture of her. That's how Gia normally looks like. The work is also done with Carlo Daniele, and you'll have the pleasure of listening to him tomorrow, I think. And last, with our collaborator, Chen-Chin Song from Shantung University. So for me, flat band physics is something that I somehow managed to avoid in my career when Professor Tasaki told us that he started looking at the flat band physics, starting with the work of Elliott Lieb. Then I also looked at work of Elliott Lieb, namely the 1989 paper that he mentioned as well. But instead of looking at the degeneracy that Elliott Lieb highlighted, I looked at the theorem on uniqueness, and that actually formed the basis of my diploma, or let's say master's thesis, many, many years ago. But in fact, my avoidance of flat band physics in many ways already started earlier, because many of you will remember that one of the first mentions of these compactly localized states in the literature, and at the time it was still called strictly localized states, was by Bill Sutherland in the context of a localization of electronic wave functions in quasi-periodic systems. And Bill Sutherland actually was my PhD thesis advisor later on. So already early on, I should have known about flat bands, but we only started looking into this in the last sort of 2 or 3 years. So since these early works, much theoretical work has been done already by people that were mentioned here, namely Andreas Milk and of course Professor Tasaki's work that we saw and heard about this morning, and many others, of course, including our hosts, namely Alexei and Sergei. In terms of experiments, we've also seen quite a bit already and heard some talks. What I like most in the context of what I'm going to talk about are those experiments which come from photonic lattices, in which I can basically ignore the interactions. And here, just to show you some examples, which you've probably seen and read about much before, are those of these photonic lattices in which Seba Mukherjee played a leading role. And you see here they made those diamond lattices that, for example, we saw theoretically in the work of Professor Aroni, and at certain energies or frequencies for the light, they find exactly the states that you would expect in those diamond lattices, these compactly localized states, and at any of the other frequencies, you don't see flat band states, and hence that was striking through. Or then they look actually at the 2-dimensional Lieb lattice, which we know is given by sort of these blue hub sites and the red, which I'm going to call rim sites. And you see they have compactly localized states on those red rim sites. For example, if you have alternating +1, -1, +1, -1, and you see that exactly those flat band stands that they then observe in the experiments as compactly localized states, whereas if they go at other energies, they see they're no longer compactly localized states, and basically much of the full lattice is sort of lighting up. So these are experimental realizations of flat band physics in 1 and 2D, in which interactions don't actually play a role. Right, so what we're going to look at is the Lieb model, but generalizations of the Lieb model. So the original Lieb model, the original Lieb lattice, is basically the one I just described before, where I have the standard sites, the hub sites I will call them, in blue. Standard because in a normal quadratic 2D lattice, that's how it looks like. And then in the Lieb lattice, you can think of it as putting these additional sites, these what I will call rim sites, I will indicate in red, putting between the hub sites. And when we looked at this immediately, it was clear to us that we can just generalize this by putting more sites in between. So 2 rim sites here in L22, and L2 then means it's a 2-dimensional system. We have 2 rim sites in between. And once you think about it like that, then obviously you can also study a 3-dimensional Lieb lattice. And that's the 3-dimensional cube, where you just put in additional rim sites between the normal group connections. And of course, you can generalize this then all the way to Lieb 2-4s and all the way to Lieb 3-4s. And these are the types of lattices I want to look at now. And what I'm going to do is I'm going to put on all those sites, basically on all those balls, I'm going to put a little bit of on-site disorder. Okay, and when we've done that in 2D, it was published in the paper to the left, and we've done it in 3D. It's published on the paper on the right, and the citations will appear, I think, towards the end again, in case you would like to take some notes of them. So we thought we were the first to extend the Lieb lattice, but of course, one is hardly ever the first these days. And it turned out then in 2017, people had already studied this system, but only in the clean case. And they derived the dispersion relations. And here I show you the dispersion relations for the original Lieb lattice all the way to Lieb 2-4. And you see that you have in the original Lieb lattice the well-known flat band. And then at Lieb 2-2, you have flat bands appearing, but now not at energy 0. They appear at energy plus and -1, and they are connected between them with dispersive bands. Lieb 2-3, you get 3 flat bands. I'm marking them like this. And you get, if I count correctly, 1, 2, 3, 4 for dispersive bands and so on. So for L24, you're going to get 4 flat bands and a set of dispersive bands sort of branching them in. So you can clearly identify how many flat and dispersive bands you have in lattices like this. So I think because these lattices are basically simple square lattices with modifications, they're at least numerically an ideal test case to study flat band physics, and putting more rim sites in is a very good way to generate more flat bands. But that's why I was so interested in Malte's talk as well, because he showed us other ways where in 2D you can basically engineer flat bands. So it may be an interesting thing to do what Malte did, and then combine it with some of the disorder modeling that we're doing to see how that affects the situation then. So just as an idea of something that I think might be really worthwhile to do. So in the 3D case, no one had done any work. So in the normal 3D extended Lieb lattice, I'm showing you here the dispersion relations. Of course, in 3D, I can't show you surfaces anymore. I just have to go via special points. Those that sort of remember the solid state physics, when we plot Fermi surfaces in 3D, we go from gamma to m to x to r and back to gamma points. And the gamma point is, of course, the kx, ky, kz equals 0. And then the m point, the x point, and the r point are given in k space by these values. And again, you see we have 1 flat band for L31, 2 flat bands for L32, 3 flat bands for L33, and 4 flat bands if I mark them correctly over here. And actually the positions you can all compute. And what's interesting is, of course, that here you have those states at plus and minus 1, and then here you get different energies, and they tend to be energies with sort of little square roots associated with them. So it's no longer as simple just as it was in the normal Lieb lattice, where you have a flat band at energy equal to 0. Now the flat bands appear sort of all throughout the spectrum. So again, this is now an ideal test case, I think, for flat band physics in 3 dimensions. And what we're going to do is we're going to put this order on it, as I said before. So at every site, and a site is given in 3D by r, which equals x, y, z, let's say, I'm going to put a little bit of disorder epsilon r on it, and the disorder shall be parameterized in the normal Anderson language from minus w/2 to plus w/2 as some form of disorder strength. So w in the following shall model the disorder strength. Okay, so then let's look at the right-hand side here. We know in 3D, in the normal Anderson model situation, we have a distribution of psi squared values as given by this colored plot. We see if the disorder is rather weak. So here, let's say disorder is 0. Disorder is rather weak, and the states basically look like they're extended throughout the whole system. Psi squared is everywhere in the cube. And then if you go and increase the disorder, so from the clean blue sky, you go to the dirt of brown, you'll see that eventually the psi squared values tend to localize around one particular region where psi squared is large, as indicated by this red cube that you might see behind all the other little cubes that you see here. And most of psi squared outside in the white region is so small that it's less than average, and I'm not plotting anything anymore. And you see what was extended then goes to something that is localized, and somewhere in between there exists in the normal 3D Anderson world a critical transition strength, WC, and you actually have a transition that you cross, and at the transition you see that you have a wave function that is called a multifractal that combines the properties of being extended throughout all space, but also being localized at particular sites. And you see some of the localization centers here a little bit by sort of these yellow plots. So that is a bit of a recap of what you expect to happen in 3D Anderson localization. And now we studied this. I'm not going to review much of the 2D case. In 3D in that paper, we again find a metal insulator transition. We look at an energy disorder phase diagram, and we try to find these critical disorder strength. And we are trying to look at what happens to those compactly localized states, particularly at low disorder. And we could have expected that maybe we find remnants of those localized states for the disorder that we can reach, which is disorder W1, which is sort of, let's say, on that scale somewhere here. We don't see much, and you should compare it with the 16.5 times the hopping strength at which on these 3D cube systems normally the transition happens. We also study the critical properties of the MIT, and we don't see any change. And in what follows, I will basically show you these results in a little bit more in detail, but then we're going to continue also, and we're going to study a different type of disorder, and that is a disorder that was made to not change those compactly localized states, so to only affect the other sites. And we'll see that there are some even more interesting results emerging. So how are you going to study most of this? Well, in the 3D case, we're going to use what's called the transfer matrix method, which is basically the workhorse for Anderson localization. And to simply explain what it does, suppose I take a system that has a certain width m, and I propagate it in one direction. I'm showing it here in the two-dimensional situation. I can write that the psi value for the future for z plus 1, if I were to call that the future in the z direction, is given by some coefficient times what is happening in the present, the value of psi in the present, minus sort of some coefficient times what is happening for psi in the past. So in this recursive way, I can construct from what has happened in the past, what is happening in the present, to construct what is happening in the future. I can rephrase this as a transfer matrix equation, which in the simple case is basically a 2 by 2 matrix. Saying that this way, And that's why some of the T's are bold. Actually, these are matrices themselves. So this is not just a number normally. This is just a number. This is a matrix by itself. This is also a matrix. This is also a matrix. But the matrix structure overall has sort of this 2x2 block structure. And then once I write it like this, I can compute what's called the localization length by basically computing the eigenvalue of the product of all these individual local transfer matrices by making a global transfer matrix out as I go in the direction in Z further and further. I can construct my localization lengths in this way. And the localization length tells me whether I am extended throughout the system. The localization length is about the size of the system, or whether I am restricted to a finite range much smaller than the system size. Now, if I do that for those Lieb models, I'm writing here the examples for Lieb 2.1 and Lieb 3.1, the situation becomes a bit more complicated. What used to be up here, basically sort of a fairly simple structure, now becomes a much more complicated structure where the original sort of, this was just some renormalized energy, now becomes much more complicated to be renormalized, has even some additional terms. And in many ways, this is what I think that Malte Röntgen did just in the talk before. And that's how I understood some of the sort of constructions that he has. We basically renormalize this complicated 2D Lieb system by taking the red sides out, and we're just left with renormalized blue sides, and the renormalized blue sides lie in the same 2D square structure as if we had the normal just 2D square lattice. It's just that the on-site energies, the on-site terms have changed a lot as given over here. If you do it for Lieb 3.1, you basically get the same structure. It's just that now the on-site terms become even more complicated, and further to the level even that this term, as you can see down here, has changed a lot as well. Okay, so this is the transfer matrix that you would normally use. Before I show results with the transfer matrix, I'd just like to tell you what happens basically when we look at the density of states. And you'll see here, this is the density of states as a function of disorder and as a function of energy for Lieb 3.1, this case. And this peak in the center here for no disorder is basically your flat band states. And then what you see is that if you increase the disorder, the flat band states very, very quickly broaden out, and already at disorder 4, and in fact, if you already look at disorder 2, you can probably say that the band has broadened, and the compactly localized states that made the peak initially over here, they've all been lost. And this picture is the same when you go through L32, L33, or L34. Let's just look at L34. We said we have four flat bands and the degeneracy, but you see that very quickly sort of dies out the degeneracy, and what you're just left with is one very broad band. So in the regime where you normally would have a transition in the Anderson case, so at 16, you should probably have lost all remnants of sort of the flat band states. I've destroyed them. That's what I would think. Let's see if this is also true when I look at the localization properties. But before we do that, just the recap of what I can do in the Anderson. I'm looking in the Anderson case as a phase diagram that schematically looks like this. In my energy, which is given in units of the hopping strengths, I will have a sea of extended states that roughly has this behavior, that it has sort of these bulges out here, that but everything remains localized once I hit a critical disorder strength. This was the 16.5 I quoted before. And as you go across one of the transitions, let's say at one of those energies, you will see that the localization lengths should diverge when you cut it across as a function of energy. You can also cut across as a function of disorder. Where's my pointer? If I cut across as a function of disorder like that. So, and I expect a power law divergence, and here the critical exponent nu that governs the divergence should be the same whether I cut across as a function of energy or of disorder, and it basically sets the universality class of the transition. So here are some results for the Anderson model. You see that this is actually true. my localization length diverges at a certain critical energy. This is not the classical Anderson model. It's a slightly different model. It's not important what different model it is, but you see sort of you get in this regime, you get sort of a critical behavior, and you can do what's called finite size scaling. You get two branches of your scaling curve, namely a so-called metallic branch on the top and a localized branch at the bottom. So I indicate the metallic wave function we saw before with the metallic branch, the localized wave function with a localized branch, and somewhere around the metal insulator transition, you get sort of this multifractal states that we talked about before. And now we'll try to do the same thing with those Lieb models. And looking at the phase diagram that we've seen here, again, I give you what we had in the Anderson model. Now this is the one that we get for L31. And you see what we're having is something that looks roughly similar. We have a sea of extended state. This is this gray region here. Outside, we have localized states, and all the way down here, and these gray regions here, and also in the other guys, these are regions which are non-accessible. Basically, there are no states out there. So we can construct the phase diagram, and then we can look at specific points in the phase diagram where we can look at transitions as a function of disorder or transitions as a function of energy and try to establish the critical exponent. In L32 and L33, you see that the phase diagrams look slightly differently. Namely, we get a sea of extended states out there from the other dispersive bands. And I mark here in L31 at -1 and +1 where the flat band states would normally be. And you see they have very little influence on what is happening overall with the localization and the phase diagram properties. Similarly, when you look down here at the flat band states, there doesn't seem to be much that they are doing. The one thing, however, is the caveat. We can only go to disorders which are above W equal to 1. So when I'm not showing any results down here, that's because here the transfer matrix in this regime basically fails. Similarly, it's about 1.5 where we can do it. And again, 1 where we could do L33. It's not that it's a failure in principle, it's just we run out of computing time to actually do something down there. So now let's see what are the critical properties and what is the critical exponent, and we do it for all those lattices, and we find that, and I've marked it here in blue, that for all those lattices for different energy or disorder transition, you basically always get the same number within the value of the error bars that you're having. There are some outliers over here and over here, but since these error bars are standard deviations only, so you expect 67% actually accuracy, and the numbers are 1, 2, 3, 4, 5, 6. So 2 should be outliers if the statistics is correct, and actually we have 2 outliers. So it all seems to be consistent. You get a value of about 1.6, which is exactly like in the Anderson case. So the critical properties of the extended Lieb models in 3D are basically the same as for the normal Anderson model. The universality class is the same. However, the transition values have changed. I told you before it was 16.5. Now it is much less. So in the L31, the critical transition happens already at 8.6. In L32, it happens at about 6. And in L33, it happens about 5. Okay, but that makes actually good sense, because basically what you're doing here is, and we'll talk about it again in a second, namely here, is that these rim sites, and that's explained down here, basically act as additional one-dimensional scatterers or localizers. We know that one-dimensional localization is very strong in the sense of being unavoidable. You can't avoid it. So if you want to go from here to that site, say, these additional 4 sites that you have in L34 just mean there are many, many more chances that you can scatter at some disorder in between, and hence you scatter more strongly, and hence you need less disorder already to lead to localization. And that's exactly what sort of this decrease in the critical disorder strength tells you, which means after all that hard work, the results are basically something that one should have been able to predict before. I mean, not quite the numerics, and it's always good to check, but it's a little bit, I mean, really boring. Okay, once we Now I misspelled him again. Once we put this under referees, we had a very nice referee who gave us a suggestion. Namely, he said, make a special disorder at the hub sites only, at the blue sites only. And that's why I make this blue in the hub sites. And don't put any disorder at the rim sites. So no disorder at the rim sites. And that should allow for the compactly localized states to survive. Once we had the paper accepted, we asked BRB to ask the referee if he'd like to join us in actually doing that. And Carlo then joined us. And for about half a year now, we've been trying to do exactly this. So now what we're going to do is we're going to put disorder only at the blue sites and not at the rim sites. And we will want to see that the compactly localized states survive. Let's see, do they do it? We're doing it again with transfer matrix. Everything should work as before. After all, it's the same lattice. We just changed the distribution of disorder, but oh God. When we did this, all hell broke loose. So I'm showing you preliminary phase diagrams computed with the transfer matrix, just as we did it before. And this is the L31 case. In the inside here, I'm showing you how it looked like before. Now I'm just showing it starting at 0 and going up, let's say here to 2. And you'll see something funny is happening. So there's a region of extended states. Then there seems to be a region of localized states. Sorry, I'm not drawing it very well. Then there seems to be another region of extended states. Then there seems to be a region of localized states. And those numbers on the disorder strengths have shot up all over this place. Instead of having something sensible around 8, 16, or even 20, now we're having numbers which are huge. Let's do it for L32. Again, we get something which is weird. There seems to be a localized regime. There seems to be an extended regime. There seems to be back the localized regime. And there seems to be something, again, localized, a drop in the center. And it is all very weird. So we were sort of stuck. We didn't quite know what to do. And we had to come up with a new method of actually doing things. And before I show you about the method, let me just tell you what happens to the density of states to convince you that we actually have compactly localized states preserving disorder. So in L21, I showed you the density of states for L31, but in L21, it looks like this. Before you see the flat bands, there's a divergence, and the flat bands basically then drop if I include my normal compactly localized states destroying disorder. But now when I have this preserving disorder, you see that basically the infinite degeneracy at energy equals 0 for LT1 survives. It does not decay. So it doesn't do this decay as it did before. Similar for L22, you see these compactly localized states, they are at -1 and +1. Again, they survive. So this disorder that we're having lets them survive. Okay, now if transfer matrix doesn't actually work, it's much harder. So how can we do it? And then it turns out from a completely different direction, something came to our rescue, namely in the context of many body localization. Oganessian and Hughes, many years back now, looked again at level statistics, looked at statistics of nearest neighbor levels. And normally when you do statistics of nearest neighbor levels and you come up with things like the Gaussian orthogonal ensemble, Gaussian unitary ensemble, and so on, you have the problem that when the density of states is variable as it is over here, or as it is over here, you have to do a procedure that is called unfolding, which can be very tricky, particularly if you have very high sort of fluctuations in your density of states. But they came up with a method, and the method is encapsulated in this blue line here, which avoids having to do this unfolding procedure. Namely, they look at what's called R-value statistics. They look at what is the minimum between two neighboring level spacings. These are my level spacings. And then look at the ratio of the minimum divided by the maximum. And because you look at the ratio of two spacings, the density of states doesn't come in anymore. You get rid of it with this ratio. And this R-value statistics is one which allows you to do level spacing analysis independent of the unfolding. And then what you observe is if you're an extended state, your distribution of these R values follows the green line, and the distribution, if you are in a localized regime of the R values, follows the black line. And here the dots and the colors are some numerical results. You don't quite know how the distribution for GOE looks like. You only have something like a Wigner surmise. You could now call it the Oganessian surmise if you wanted. For the Poisson behavior, you have something exact. But nevertheless, what you can do is you can look at the mean of the R value in both cases, in the GOE and then the Poisson case. And when you do that, you see that there is a clear distinction. Namely, in the GOE case, you get 0.53. In the Poisson case, you get 0.38. And then if you study it for different system sizes, a drop from about 0.53 to 0.38 or 0.4 indicates a transition from extended to localized behavior, which is what they used in many body localization. So let's do the same in our case. First, let's test that the method actually works. And that's what we did. This was our transfer matrix based phase diagram here on the left. I'll repeat it again. Now we'll do it in this R value statistics. And I'm showing you as a function of energy and disorder, very fresh results just from last week. Carlo and Gia, I don't think have seen them yet. And I'm showing you in this color scale, basically what is the value of GOE, and that is this red that we see over here. And what's the value of Poisson? This is the black in this guy. And you see there is in the center, roughly where the phase diagram on the left is, there's in the extended regime, you have this sort of behavior that you see on the left. And the rest is all localized over here, just as it was localized here. And that left guy has been computed for n equal 10, right guy has been computed for m equal 20. And when I say m equal 10, 20, this is number of unit cells. So actually number of atoms is 3 times that. You have to take it to the power of 3. So behind all this is diagonalizations of many, many, many systems, a few hundred each, at different values of energy, different values of disorder, and then computed the R value for all those guys. So there's quite a bit of actually numerics behind it. And you can see we can reproduce the phase diagram that we had before with the CLS, the compactly localized states violating disorder. And finally, this is what happens in the CLS preserving disorder. And these are the first results, again, just about a week old. And they are very interesting, I think. So again, as a function of energy and as a function of disorder over here. Remember, we had before disorder 100 in the TMM. So now we see something fairly similar on a scale. And again, red shows me where is my extended states, basically. Blue shows me where is my Poisson value, so where are my localized states. The left is for m equal 20. The right one is, sorry, left is for m equal 10. The right one is for m equal 20. And now we see some funny stuff. Namely, we see that this is, I should have done it, I should have written it down. This is L31. So this is a 3-dimensional ender with one 3-dimensional Lieb model with one flat band at energy equal to 0. So you clearly see something special is happening at energy equals 0 in both cases. On the right-hand side, you probably see it best. These compactly localized states still somehow survive at weak disorder. We're having something which is very close in value to the Poisson value, the Poisson mean, it is blue. Outside, we have a regime of extended states. And then there seems to be a region where it's not quite clear to say what is going to happen, particularly if we go to large system sizes. And then there seems to be something really funny when we go to large disorder, because somehow these compactly localized states get an R value, which seems to be fairly large. I'm not quite sure about it, but if you're looking at in detail, so first interesting thing is when we have a regime like this and we go from weak disorder to larger disorder, we're basically cutting from something which initially seems to be localized into something which is then extended over here and becomes localized back again. This is known in the literature as an inverse Anderson transition, and I'm only aware of one paper that did this a couple of years back, I think 5 years back. We may have a situation where in these Lieb models we can observe an inverse Anderson transition. then these compactly localized states seem to stop the delocalization at the flat band energy here. This seems to be a regime which is localized. Will it survive if you go to larger system sizes? I don't know yet, but indications are. And why do the compactly localized states, or at least in the vicinity of the compactly localized states, show R values which are valid for the Gaussian orthogonal ensemble and which should indicate extended states? Is it simply a case of superpositions of these compactly localized states, which may be, oops, I hit the wrong button. Oh, I did something I don't want to do, which may nevertheless be interesting to understand what is really happening. And hence, finally, we've hit on a model which we think, at least I think, is no longer boring. It's quite interesting. And I like phase diagrams that look a bit weird, and because they can be interesting challenges, for example, to those photonic lattice people before, if they can actually find those things. Okay, with this, I come to my second and last set of conclusions, namely, so the boring stuff isn't holding anymore. So let's forget about this. Now we can say the flat band states changed the phase diagrams, and we still expect the universal properties to remain unchanged, but nevertheless, studying this sort of inverse Anderson transition going this way may be interesting to see, because these compactly localized states, I think, are localized for a different reason than Anderson localization. And hence, this transition along this line may be a different transition than the normal Anderson transition. Okay, at the moment, we still expect the universal properties to remain unchanged, but it's just an expectation. They might very well change. So the rim sites in the Lieb model, again, okay, in the normal Lieb models with compactly localized states, violating disorders act as additional localizers, and overall the compactly localized states preserving disorder is weaker in terms of the critical disorder has to be larger to actually get somewhere, and stronger because it can lead to an inverse Anderson transition. So there's much more work needed to fully understand that. And in the long run, I'm hoping that I get lucky, namely that maybe some people find that these systems actually exist in nature and don't have to be engineered like these photonic lattices. And with this, I thank you very much, and I'm at the end of my talk.
Thank you very much for the very interesting talk. So now we have some time for a couple of questions. Okay, Professor Unknown Aroni, please go ahead. Unknown Aroni. Yeah.
Hi, Rudy. Thank you for your talk. This is a question I asked you already a few months ago. I wonder if you looked at that. You can start from your Lieb model, and then you can eliminate the additional sites on each bond to map the problem back onto the square or the cubic model, a hypercubic model. And then in this renormalized model, you will have renormalized site and bond energies. And you can look at the distribution of those new random variables for the original square or cubic model. And if the distribution of that maps onto a distribution of the usual Anderson model in some sense, then you would expect the same universality class, and you would be able to predict the new transition point from that renormalized distribution. Has that been looked at?
Yes and no, because it's not quite as simple. Let me point on the pen again. So, oops. So, of course, what you said is basically what we're doing here, right? I told you we renormalize the red sites away, and then we get back to the old structure, but now the blue sites have all been renormalized. But when you look what is actually happening, you'll see what you're constructing in this renormalized disorder is a correlated disorder, because the sites at X and Y are now correlated with the neighboring sites. And
yes, also the sites and the bond variables are now correlated.
Yes, so it's the on-site term which is correlated, but it's also the hopping terms which are correlated. So you're getting a correlated disorder. So you're not getting back the old Anderson type of disorder. You're getting a new disorder distribution which is correlated. And in fact, this is an age-old problem that I've discussed with Israel and Felix Israelev many years back, because if you think about what you're doing when you numerically diagonalize a three-dimensional Anderson model, you put it into tri-diagonal form, which means you give it effectively a one-dimensional structure. A tri-diagonal matrix is like a one-dimensional Anderson model, however, with renormalized on-site energies and renormalized hopping strength. And then you could say, so a one-dimensional Anderson model doesn't have a metal insulator transition, so how the hell can you map a 3D problem to a 1D problem? But the only way you can actually do it is because in this 1D mapping, you have correlated disorder. And we know for correlated disorder, you can even in 1D get a transition, right? So if I were to do what you just said, I can do it, but what I effectively do is I have highly correlated and not trivially correlated disorder. The distributions are basically different.
Yeah, so I can rephrase your results by saying that what you showed is that the universality class of the Anderson transition is broader than we thought before, because the original exponents were derived only for the simple distribution of the site energies. And now you showed that correlations do not affect the universality, because even in this correlated model, you get the same exponents.
Yes, but I would say these types of correlations, there could be other types of correlations, let's say truly long-ranged ones. These are as long-ranged as the rim sites are. So for L21, where we have one rim site, it's the nearest neighbors. But if I go to L24, there would be 4 nearest neighbors which are correlated. But of course, if I do properly long-range correlated ones, things would again be different. So you could say if you include correlations which are short range, then you can real normalize them away, and I would still be getting the same universality class. But at least in terms of phase diagrams, they change and they become, and they look much more interesting, right?
Thank you.
Okay, Alexei?
Okay, yeah, thank you for the nice talk. And I have quite a bunch of questions. The first thing is I probably misunderstood, but in the case where you only add a hub disorder, I believe the compact localized states are just there no matter the disorder strength. So at zero energy, you should always see localized states. They're simply not affected by the disorder, or am I missing something?
Yes, that's the stuff that you see here, right?
Mm-hmm. Yeah, so then why do you see the large R ratio? So
I don't know. I don't know.
Well, I mean, my only explanation would be that then probably for these large disorder values, you start washing the dispersive band close enough to the compact localized state. They probably try to do something, but they cannot because these states are protected.
So first of all, I should tell you, I'm not computing exactly at the energy of the compact localized states. So yes, I'm not computing exactly at E equal to 0. I'm computing a little bit outside at 0.1. Right?
Yeah, that makes sense.
Right, but it's still interesting to see. So somehow do these compactly localized states do something to those states which are close next to them? Like you said, this washout effect, is it really there? Or is it something that I only have because of finite system size? I would have expected I see nothing there, right? And I see something.
I'm not sure, because these states are protected, so they might well act as a wall that the states cannot penetrate. And so that might well be the explanation. Okay, I have another question that is purely technical. So when you mentioned sparse diagonalization, I presume this was Lanczos.
So we're using not Lanczos, we're using Jadamilo, which is Jacobi-Davidson based iterative method.
Okay. No, I'm just curious whether but technically it's still based on the same trick, shift invert, or
yeah, it's shift invert based, but with an iterative solver of the shift and invert. That's
Okay.
why I can't look directly at the flat band states, because the degeneracy is so high that any sort of recursive iterative algorithm has a problem there, of course.
Okay. And at this point, I was just curious whether you have considered the what is it called, the polynomial filtering technique that have recently been proposed to basically circumvent the shift invert, the bottleneck that you have to solve the linear system. So they avoid that. And that seems to, I mean, at least in some cases, it seemed to allow to go to yet still larger system sizes.
No, we haven't. I'm not perhaps even aware of the work. If you send me the reference, I would love that. But keep in mind, even here, you might think that the system sizes are small because I quote 10 and 20, but really it's you should think of it as a 30 cubed and as a 60 cubed system.
I remember
right?
that.
And remember also, we're not looking as we did when you look at multifactor states. We're not looking at a particular energy. I actually have hundreds of points in the whole region down here, right? Because I need to sample the energy, I need to sample the disorder, so that I can actually get those phase diagrams. Of course, the next step that we want to do will be, once we have this phase boundary roughly nailed down, if you can see my pen again, once we have it nailed down, we will stick at some energy, we'll just cut in this direction, we'll cut in this direction, then we'll do high precision runs, and then we may want to go to larger system sizes. But I think even with the existing code, we can do that there, because then we want to do scaling and get critical properties and all this.
Okay, yeah, but I mean, this filtering technique is basically a modification of Lanczos. It does the same, except I believe it does it either faster for the same system size, or you can go to larger one because you don't have to solve the linear system. Okay, I'll send the reference. Yeah, so the other question is actually related.
Alexei, so we are a bit behind the schedule. So could you,
could you be
yeah,
I'll ask.
Yeah.
Oh, well, I'll probably ask after the session is over.
Oh, okay. Thank you. So I think it's time to move on. So let's thank the speaker once again for his nice talk. Thank you very much.